All right, so let's see the proof. So we are just claiming that under this condition that the gradient or differential of G is not zero at any point of a level surface, the level surface is indeed a surface in R3. Let's see the proof. So take any point P in no, not P, Q in M. Then of course Q is just what? Okay. Then since dg at P is equal to, what is this? Differential of G at P. Maybe I can write it this way, right? Differential of G at Q. What is this? This is just derivative of G with respect to X at Q dx plus derivative of G with respect to Y at Q dy plus derivative of G with respect to Z at Q dz. So this thing is not zero, means that either this derivative or this one is not zero, right? One of them is not zero. Okay. All right. Right. One of them shouldn't be zero because the assumption that this differential is not zero at any point. So one of these derivatives is not zero. It is from R3. It's the differential of G. Yeah. Okay. Well, one of the partial derivatives is not zero. Without loss of generality, let's choose this one to be non-zero. Del G over del Z is not zero. Without loss of generality, let's assume that this partial derivative is not zero. Well, then we have what? You see, I have an equation like this given by this function, and the partial derivative at a point Q is not zero. That's the assumption of implicit function theorem, and of course we are assuming that G is differentiable, right? As many times as we want. If this is the case, then by the implicit function theorem, this equation can be solved in terms of X and Y, right? That's the assumption. If this derivative is not zero, it means that you can solve Z as a function of X and Y. Moreover, that function becomes is a differentiable function. So by the implicit function theorem, there is some f, okay, defined on some region D into R, so that the point D is in R2, and your point Q is in D cross R. Yeah. You're right. Okay, yeah, it's C. So there is such a function so that okay, I already said so that with the satisfying which condition? This one. G of x, y, and then f of x, y is equal to C for all x, y in D. So what happens is the following, right? We have this point Q in the space, here is the image of this point in the xy plane. So this is the xy plane. This is the z-axis. I can find an open set here, some D, so that and a function so that the solution of this equation gxyz is equal to C is the graph of a surface, right? So it's the graph of a function, sorry. It's the graph of a function like this. So this is the surface z equals f of xy. Okay. Well, of course, right, implicit function theorem guarantees existence of such an open set. Right? This is an open set in R2. And f is a differentiable function. I don't write specifically that f is differentiable and so on, but they are clear from the implicit function theorem. Now, what is the surface patch then? Then x from D into M, which is a subset of R3, given by x of uv is equal to what? Just this formula, uv f of uv. uv f of uv.
Hocam,
Evet.
tarihini değiştirebilir misiniz?
Tabii ki. Kusura bakmayın. Well, then this function given by this formula provides a surface patch. For M, which is G inverse of C at the point Q. Okay. Why this is a surface patch? Because we already proved that, you know, graphs of smooth functions are surfaces, right? So once I have this f from the implicit function theorem, I can write this formula, and you see that, you know, this point is already in M because it is the definition of M, right? M is the point set of points where G u v f of u v is equal to C. Okay, now this is a surface patch. We already proved that. Therefore, this thing is a surface. So this finishes the proof. Now let's see how that theorem provides another way of seeing that this surface, this subset is really a surface. Okay, now consider, so this is an example, another example. Sometimes the camera is got frozen. Okay, so another example. Let sigma be the surface. Consider the function g from R3 into R given by what? Okay, g x y z is equal to x over a squared plus y over b squared. Okay, which is a differentiable, you know, nice function from R3 to R. Yes, and okay, note that then sigma is what? This is just G inverse of 1, right? So I just let C equals 1, C equals 1, then inverse image of 1, right? The points where this is equal to 1 are the points exactly, you know, these points, right? Because uh, if x, y, z is in G inverse of 1, then x over a squared plus y over b squared is equal to 1. So that how can you parameterize something like this? It means x over a is just cosine u, y over b is equal to sine u, right? For some u in R. So F inverse of 1 is equal to what? X coordinate is just A times cosine U, B times sine U. And what about the Z coordinate? Z coordinate could be anything because, you know, this function is independent of Z. So it can be anything, right? Here U and V are just real numbers. But this is nothing but the surface sigma. So this way we see that sigma, which is this surface, is actually a surface in R3, right? Because, well, I should write not F but G, because sigma is the inverse image of a function whose gradient is not zero at any point. So I didn't show that. Let me show that. Okay. We must check this. dg is non-zero on G inverse of C. In this case, 1. Well, let's see. What is dg? dg is just G is this function, right? G is this function. What is the differential of this? Derivative of this with respect to x. So it is 2 times x over a plus derivative of this function with respect to y. So I have just 2x over a dx plus 2y over b dy. Okay, I claim that this is not zero at any point on this surface. But if you are on this surface, note that if Q, which is x, y, z, is on the surface, then x over a squared plus y over b squared is equal to 1. So that either x over a is not 0 or y over b is not 0. So that either x over a is not 0 or y over b is not 0. Therefore, the differential is never 0. Is never 0 on the surface. Okay. Okay. Another example of a surface. One more example. Kamera kaldı. Haklısın. Zoom'dakiler de uyarmaktan bıktılar. Haklı olarak. Okey. Şuradan büyüteyim birazcık. One more example. So-called surface of revolution. All right. So what is this? Let C be a curve in the XY plane. And let us rotate the plane in the YZ, along the x-axis. So consider the revolution of R3 about the x-axis. The surface swept by C is indeed a surface in R3. So what we mean is this. Let me draw the plane like this. Sorry, this is the z-axis, x and y, and x and y. I take a curve in the xy plane. So let's say this is our curve C, okay, in the xy plane. What is my surface? I take this curve and rotate about x-axis. I rotate the whole, actually R3 about the x-axis. Then this curve will sweep a surface, right? Something like this. Okay, so it will be something like this. Belki bu kadar değil. Okay. And here şunu kötü çizdim. Şöyle yapmak lazımdı herhalde. Okay. So this is the surface swept by the curve C. So C is this curve. I just rotated about the x-axis. Haklısın, olsa iyi olur. Öbür türlü smooth surface olmaz, değil mi? Okay. Evet, evet, evet. Okay, so if C is the image of a smooth or differentiable one-to-one function, let's say sigma from interval into R2, okay, let's say given by T, I don't know, okay, sigma 1T, okay, let me say UTVT. Yok, bunu da söylemek istemiyorum çünkü değil mi? U'la V'yi de başka şeye saklıyoruz. Şöyle yapayım. X, Y desek sorun çıkar mı? Yani birebir bir fonksiyon olsun. Yani arkadaşınızın dediği şey şu. Şöyle bir şey olursa if the image of sigma is like this, if it is not one to one, then when you rotate this, you will get what? You will get not a surface, but so there will be some, you know, balloon like this, and it will be just around the whole surface. Okay, so you have like bir tane torusu buraya yapıştırmışsınız gibi olacak. Right? It will be like a torus, like a tire, just glued onto the surface. Okay, and the whole thing won't be a surface then, because it is not locally Euclidean. Yeah, simple. So if we just assume that it is one-to-one, that would be fine. Except maybe at the endpoints. So we may allow the following. We want this function to be one-to-one. So sigma is one-to-one on AB, the open interval. Okay. At the endpoints, it might be a closed path. So C could be something like this. C could be something like this. In that case, when you rotate this about the x-axis, you will get a torus, right? So if this is a circle like this, when you rotate this about this axis, you will get a torus. And in that case, your function is not one-to-one because the endpoints of your curve are the same, right? It's a closed loop. Okay, now, so what okay, what is the surface swept by this curve C? So let sigma be the surface swept by the curve C. How it will look like. So if I have a point in the XY plane and I rotate this space along the x-axis. This is the x-axis. What would be the, so if I rotated this a little bit, so I mean this, so this is, let's say, theta, right? So I take this and rotate theta radian. What will be the coordinates? X coordinate won't change, right? X coordinate won't change. YZ coordinate, so this is the YZ plane. In the YZ plane, I rotate this point. Yani şöyle, you may think it this way. In the YZ plane, I have this point, and I rotate this, let's say, theta radian. What are the coordinates here? Coordinates are cosine theta and then sine theta, right? Maybe I should write y in front. So then this will be what? X coordinate won't change. So this point is what? X and then y times cosine theta and y times sine theta. No, I think this is correct. So the points, a typical point is this. X, y cos theta, y sine theta, right? Here, of course, X and Y are like this, right? X and Y are like this. So X comma Y is in C, and theta is any angle between 0 and 2 pi. Right? I have a point here. So this is a point on the curve C. I just rotated theta radians, theta changing from 0 to 2 pi. To write this as a surface, maybe I may do the following. You see, X and Y are functions of T. What are the variables here? T is changing, so that this point is changing, and theta is changing, the angle. So my variables are T and theta actually. So let me take them as U and V. My parameters for a surface parameterization are rather U and V, right? So I can write like this, X. So it is X sub U, and then Y sub U times cosine V, and then Y sub U times sine V. U is in the interval I, and theta is between 0 and 2 pi. So this is my surface patch. This is my surface, and surface patch is what? Surface patch is given by this formula, right? Tabii surface patch için x ile yazarsanız başınız derde girecek. Çünkü burada x'i kullandım zaten. Neyse. Okay. Hı hı hı. Şimdi tamam değil mi? V is the angle. So this is V. And T is just U. A special case is special case. Suppose C is the graph of a function y equals f of x. So in the x y plane, C is the graph of a function. So this is C. And
Hocam,
I
tahtayı
okay.
teşekkür.
So let's see this special case. C is the graph of a function, let's say of f of x, and then I just rotate this, right? So we get something like this. So this will be my surface, sigma. And what will be the parameterization? What will be the parameterization? What are the variables? Variables, so xt, yt. Here, a point here is just, I don't need to use, xt, yt. I can just write u and then f of u, right? I have this point, u, f of u, and then I rotate v radian. So our surface is just what? Okay, x of u is just, it is just u, and then y of u times cosine v. Y of u is just actually f of u times cosine v, and then f of u times sine v. U is in the interval I, and v is in 0 to pi. Yani, so when it rotates, you'll be at a point like this. So this point is just u. Okay, so let me say this is the point q. Q is just u, f of u cosine v, f of u sine v. Okay. Okay, let me raise the board. another example of a surface of revolution. All right. Sorry, z-axis, x, y. Let's take a circle here. Let's take a circle. Okay. This is not a graph of a function, right? This is a circle. Let's say with center at the point A, B, and let's say it has radius R. Okay. When you rotate this about the x-axis, you will get so-called a torus, right? Something like this. So this is the circle here. This circle. I have this. Yani belki bunu böyle çizmek yerine şöyle çizsem daha iyi. Okay, so I have this circle here, and just it is this circle, let's say C, and rotated about the x-axis. So this is my x-axis, let's say, and it is rotated about the x-axis. Okay. This is called a torus. Okay, torus. It's the surface of a simit, right? Or donut, or bagel. If you do half twist, you may get non-orientable surfaces. You know, consider this. Half twists. Take a line segment like this. So this is our curve C. Okay, just a line segment. Şöyle bunun etrafında dolaştıracağıma göre. Okay, consider this line segment. I rotate about yok bu half twist olmuyor. Yani half twist değil de şöyle yapayım. What I do is this. I rotate along the x-axis. I also rotate this line segment, okay? So that when I complete one revolution, this line segment will be turned 180 degrees. So I take this and I start rotating about the x-axis, but while I'll do that, I just also change the rotate the line segment, okay? And when I got back to the original position, this will be turned the other way around. What would you get? Yani şöyle bir line'ınız var, değil mi? Bu line giderek dönüyor. So you may think it this way. You have a so these are the intervals, okay? But you will glue back the two ends. However, this will make a half twist. Okay, what will be the result? The result will be a so-called Möbius. Let me draw it like this. Okay, so here is my interval, let's say C. I make a full turn like this, but while I go along this curve, so şöyle dönüyorum yani, my interval, which let's say points upward here, you see this end comes here and this end comes here, so it becomes like this. Okay, so if you do that, you get a Möbius band. It's also a surface, okay? It's also a surface in R3. Okay, so let's stop.